said something. Cheerios, my friend, cinnamon toast crunch. Cinnamon toast crunch it is.
So you guys would actually rather watch the video than listen to Dan talk? Well, unfortunately, you can't stop Dan from talking no matter how hard you try, believe me. I know this quite well, particularly 2 or 3 in the morning after a bunch of shots of tequila. Used to wind him up and let him go. But for those of you that don't know Dan, which I can't imagine that you would, Dan Kaminski is a good friend of Toorcon. He's actually top of our buddy list. So, and he's been talking with Toorcon for a long time, actually. We're particularly pleased that he's a solid presenter with us. He always takes the time out to be here for Toorcon. And he's going to be talking on his Black Ops with, I guess, pattern recognition, the Toorcon remix. So let's give a big hand for Dan Kaminski.
If you need any more, my friend, right there.
You're a sick bastard, Zane.
Hi. So, we're here to break stuff. Cool. My name's Dan Kaminski. I've done like a couple books, worked at a couple companies, broke some stuff. That's about all that matters. You know, I'm really supposed to change what it says at the top of these slides. But yeah, so gold mitt. I suck. Oh, the drinks are coming. So there are actually times where I'll talk about a single subject like DNS, and I'll just focus on DNS like a laser and just totally stay on that one topic. No, not this year. This year's all about ADD is useful. You get to work on like 8 things at once and then go ahead and present at the same con. So we've got lots of things to talk about. We're going to talk about network neutrality. We're going to talk about what happens when you do yet another massive internet scan and find 2 million SSL servers. We're going to talk about online banking. There's a really trivial hack against most online banking systems, actually specifically 27% of the top 50. It's just depressing that this hack exists, but potential solution for it. I kind of sort of did some patching to OpenSSH a few years back that kind of sort of left us in there. So I'm going to do a really hideous fix to fix that. But the big thing, of course, pattern recognition. Let's make some entropy recognizable. Humans are pattern recognition engines. It's kind of what we do. The degree to which we're using our human abilities for pattern recognition to actually go after code is, let's just say, a field that could be expanded. And thus achieving my, my grand goal of pretty picture. So, let's begin. Oh yeah, speaking of pretty pictures, yes, you can diff 2 files visually, visual bin diff. And I'll show you how to do that later. Okay, so we got to talk about network neutrality. You guys are a pretty cool crowd. I'm not going to go into too much of the politics. Suffice it to say, telcos are looking at traffic and going, well, we can't make more money making the network faster. Maybe we can make more money making the network slower. Yeah, there's this great quote from Comcast. To accommodate the needs of our customers who do choose to operate VPN, Comcast offers the Comcast at-home professional product. This product will cost $95 a month. I don't want to spend $1,100 a VPN into work, thank you very much. It works fine just right now. So, how do we actually find stuff that's going nasty against network neutrality? In terms of definitions, network neutrality is all about your ISP taking a look at the traffic you're moving and applying different qualities of packet transmission based on whether they actually want the packet to route or not. There's an interesting question. How do you know if your quality of service is being degraded? So I was working on something totally different. Just a random little TCP stunt. I like TCP IP. I like messing with it. And I sort of realized we could start using this for network neutrality. All right, so here's the stunt, right? TCP, standard mechanism for communicating between point A to point B with a reliable stream of packets, a reliable stream of data. TCP automatically determines the amount of available bandwidth between any 2 points. There is no communication between all the various users of the same line. What happens is when the line has too much traffic, it just drops them on the floor. And TCP's job is to detect packets being dropped on the floor and slow down. If it doesn't slow down, if no one slows down, then the line becomes useless, and that sucks. See video on internet. So dropped packets on the internet are actually a source of information about not just your own session, but about other things that are going on the channel. And so what you can actually do is, well, so here's the concept. TCP line, figure if TCP determines that a given end-to-end, hang on, let me think this out for a second. All right, you're talking with someone in Finland. They're not 1 hop away. You've got maybe 15 hops between you and Finland. What TCP is able to do is figure out, if I send packets at 1 kilobyte a second, will they get all the way there? Great. 10K, great. 20K, great. 25K, no. There's a certain amount of available from one point to an end that is basically the, you get it's the weakest chain thing, right? The maximum amount of bandwidth along the link, is constrained by the slowest link. So what you do is, I'm not saying I'm hungover from last night. I'm totally hungover from last night. Or maybe I'm like pre-hungover for tonight. Oh man. Maybe I should actually put back on the Pirate Baby thing and go sleep under the table for a bit. Okay. All right. I can do this. Professional. All right. So, TCP tells you that you can only send traffic at 5 kilobytes a second. It tries to send it faster, packets drop. So what do? You send packets faster than 5 kilobytes a second. But Dan, you say, this will cause packets to drop. Yes, it will. If those packets make it all the way to the hop with the constrained bandwidth. You send 5K a second on your TCP stream. Now you start sending more traffic. On a separate, completely separate session, you start sending another 10K a second. But you only let it go 1 hop. Will it cause any traffic to drop? No, not unless the weakest link was between you and 1 hop away. So you are now sending 15K a second out of your Ethernet port, but only 5K a second all the way through the internet. 1 hop, that's still going to make it. 2 hops, 3 hops, 4 hops, 5 hops, 5 hops. Now suppose you've hit the hop with the constrained bandwidth. At 5 hops per second, TCP had detected you had 15K of capacity. You are sending, TCP had detected you had TCP detected 5K of capacity. You're sending 15. What happens? Packets drop. So what's interesting here is you're seeing this feedback on your TCP session. It is being caused by something in the TCP session. It is being caused by you sending this additional traffic. You know which hop is getting that additional traffic, and you know that it is causing failures because you're seeing it in your TCP session. What if we start injecting traffic from different locations? What if we start injecting a bunch of traffic from different IP addresses? So I have a TCP session going on, and YouTube tries to send a whole bunch more data. Will there be different reactions than if CNN starts sending a bunch of extra data? Will there be different reactions if it's a bunch of encrypted data? How do you actually do this? What does this actually look like? So this is, new slide for Toorcon, rock on. This is how you actually do this. What we're going to do is we're going to go to our random number generator. We're going to monitor how much data we can get through it. We're going to pipe it into SSH, because if you know me, everything has to work through SSH. And what we're going to do is we're going to see how fast can I send traffic to this particular host, just normal. Actually, this is, okay. So I've got some session going on, and I'm basically filling. TCP has detected a 380.3 kilobytes per second average stream. That's how much can be pushed. I have achieved TCP saturation. TCP has said if I send it any faster, things are going to die. I start sending another 100K a second. I only let it go 5 hops. It's still going at 380, 390. Now I let it go 14 hops, and it down the original session. So HPing is a very flexible tool. I can go ahead and, using the -A flag, change my source. Using the -P flag, change my port. Using the -E flag, change the file content. So essentially, I can inject a whole bunch of additional traffic and see, is it causing the drop from 390 to 188? This is actually useful if you're trying to figure out basically what you're doing is you're figuring out what the network is defining as interference. And in defining what the network is defining as interference, you're able to figure out what is what its standards are in terms of neutrality. If YouTube can get more packets through, but CNN can't, then the network is biased towards YouTube, which is actually the point I was trying to make a while ago. Here's a bit of a stunt. What if you want, so this requires saturating a line with TCP packets. Maybe you don't want to do full network saturation. Maybe there's a problem with that. Maybe you want to get better data, performance status, what's the jitter, what's the latency on packets. This is more detailed information that you can extract using the method I just described. So let me tell you what I'm actually working on. This is, I think, the first public time I'm talking about it. It turns out, I know this is shocking, Windows Media Player actually has more code in it than just DRM. I had no idea. That's all they're talking about. But no, there's actually like a full-on video infrastructure in there. So check this out. This echo is getting a little bit to me. Okay. So Windows Media Player, when you're sending video, and Real Media does the same thing. I think QuickTime has an RTP mode as well. When it's sending you video, it just does a unicast UDP stream. It just fires video packets at you. Now, what's saying earlier that if you just fire packets out, then you're just going to cause bandwidth overload, and there's no feedback, and you don't know that you're actually overloading the network, and all those kind of good things. Well, yes, that will all happen, and that is why we have another protocol called RTCP, which actually sends back jitter information and bandwidth information and allows the media playing infrastructure to figure out how much bandwidth is available. There's actually nothing that forces, this is kind of fun, there's nothing that forces the RTP stream, the RTCP stream that says quality, to go back to the same IP address that appears to be sending video. So we can have packets that appear to be coming from YouTube, appear to be coming from CNN, appear to be coming from all these places around the internet, and we're sending back performance data to Dan Kaminski. Cool. So, no, really, I'm kind of putting these guys on notice. If you're doing nasty things to filter and to provide bias towards one or the other, I'm going to find you, I'm going to bust you. So please stop. Now that we're done with that, SSL. So yeah, I have my big scanning box, and I threw it a while ago at, let's find every SSL server on the internet and say hi to it and collect its certificates. I run this system